Once again, AP Calculus BC students, we are actually recording live from my Period 2 BC class. Can I get a hand? Yay, calculus. That's the kind of enthusiasm that we want about calculus here at Avon High School. We are in the Larson textbook, 9th edition, chapter 9, section 10, tying up all the loose ends about Taylor and Maclaurin series. And in example 2 in Larson's book asks us to do something about a Maclaurin series for sine of x that we actually, I believe, found in the previous example, number 1. Now, before we embark on example 2, I want to spend just a moment looking at what theorem 9.23 says, convergence of a Taylor series. Now, what we've got here is it says that if the limit as n approaches infinity of r of n is equal to 0. All right, well, let's just pause there for a moment. Rn, what does Rn mean? We have to think back to that. Now, if you use a different textbook, obviously this might be a little bit different for you, but in the Larson textbook, Rn refers to the remainder or the error, right? And if you think back a little bit further into some of your discovery in BC calculus, you may have recall that you dealt with an Rn value that stood for a neglected term, the first neglected term, after which you have added a few members of your sequence. So they can all pretty much mean the same thing in this example that we're about to embark on. Okay, in just a little bit, I will remind us all what the Rn formula is in the Larson textbook, the way that it's written. But in any event, if they're saying that the limit as n approaches infinity, that would be the number of terms in your sequence, in your series, of this error term, this remainder term, this neglected term. If that value is 0, well, what does that say? Well, it says that there's no error, right? So that means that that function would be pretty darn reliable. So darn reliable that the f of x will have exact equivalence to the power series, or in this case, a Taylor series. Or it could be a Maclaurin series if you are indeed centered at 0. Okay? Let's see if we can put all this here together. For number 2, we've got our function f of x equals sine of x. And if we recall, we developed a power series for this. We developed the Maclaurin summation expression for this. And I believe it looked something like this. The summation as n goes from 0 to infinity of -1 to the n times x to the 2n plus 1 all over 2n plus 1. Now, if you have trouble with that, I would suggest that you could look not just on my channel, but you could look on just about anybody's YouTube presentations or outside of YouTube for that matter, and just Google search sine of x Maclaurin series, and you can see a nice representation of this. All right, next, we got to deal with this Rn. What is the formal definition of this R sub n term? Well, according to the text, R sub n for any term x wants to be thought of as a positive. Let me fix that here. We want to think of this as a positive remainder, a positive error. Therefore, we know that it's going to be something larger than or equal to 0, right? If the remainder was actually equal to 0, that is all the better. That's kind of what we're going to strive for here in this case. And that is equivalent to, if you recall, that neglected or term, that value in that term that comes next, which would be characterized by the nth plus 1 derivative evaluated at some place that Larson calls z. Other textbooks use other numbers or other letters, times x, in this case to the n plus 1, because we are centered at 0. This is a Maclaurin series. so I don't have to put an x minus c there, to the n plus 1 power, all divided by n plus 1 factorial. That's the definition of our remainder. Now, what we're going to have to do is focus very intently on this fn plus 1 derivative at z. That seems to always be the problem. It's a problem because we can't really find this elusive z. If you remember, we recall that z is something that might lie between c and x. Right, now that's provided that c is left of x, because it certainly would make just as much sense if it was written the other way around. But the big problem here is, yes, while we might know c, we have absolutely no information about x. In fact, we're going to try to show that this is true for all x down the road. So not being able to figure out what x is makes it doubly difficult to figure out what z is. And even if you recall, if we did know what x was, we still had a hard time finding z. So what are we going to do about that? Well, we just think about, what does fn plus 1 derivative behave like? Well, the n plus 1 derivative of f evaluated at z is going to be one of just a few things. And I'm going to ask my class, what do you think? What do you think the nth plus 1 derivative of this sine of x function is going to spit out? It could possibly spit out, well, we're not evaluating it anywhere, so it wouldn't be 1. The derivative of the sine of x could be, well, what is the derivative of sine? Cosine. What's the derivative of cosine? Negative sine, derivative of negative sine, et cetera, et cetera. So if I recall, then I think there's only 4 different outcomes. What would they be? There, you got it. You're either going to get positive or negative sine of z in this case, or positive or negative cosine. Make sense? So that's any of those 4 would be fair game for our n plus 1 derivative. Of course, we don't know which one it's going to be because we don't know the value of n. All right. Now, I'm going to get rid of this because I'm going to need this space in just a moment. Now, what we're going to do is take sort of the worst case scenario. And what we'll look at here is that at most, the worst possible value or the highest possible value of our nth plus 1 derivative evaluated at some z would be equal to 1. Exactly. Your sine or cosine can never go any higher than 1 in this case. Most likely, for other values of z, you'll get something that's less than 1. But do you see that at the very worst, this absolute value inequality has to be less than or equal to the exact same expression with the f of n plus 1 derivative done away with, right? As you can see, yeah, whoa, there's something missing here, right? I took away the nth plus 1 derivative of f. Well, why did I do that? Well, because I'm saying that this expression has to be less than or equal to this expression for whatever value of that f of n plus 1 derivative is going to take, all right? Even if that f of n plus 1 derivative is exactly 1, well, we could say that we're equivalent. But if that f of n plus 1 derivative, let's say it was less than 1, which it very likely might be, then we can definitely say that the less than would be true. Okay? So what really becomes our goal now is to focus on this absolute value expression and figure out what its limit is going to be. Okay, and fortunately that's going to be very easy. Let's extend the page here a little bit and focus on the limit as n approaches infinity of the absolute value of x to the n plus 1 over n plus 1 factorial. Well, I don't want to make this any more complicated than it has to be. I know that my students and I have talked about this time and time again. Take a look at this denominator very carefully. Then take a look at the numerator. Who is going to take off faster? The denominator. Factorials seem to outrun exponents in every single case. So you're going to have a denominator that gets much bigger, much quicker, which means this limit will end up being 0. And that's a good thing. That's kind of what we were setting out to prove. Okay. Now if we go back here, if we go back to this entry that you see here now, I know I've got a lot of notation on this, but I just don't think I have to rewrite this to get you to all understand what's happening. We have just stated that the limit of this expression is indeed 0 as n approaches infinity. Well, if this becomes 0 and our Rn is between what two numbers? 0 and 0? What does that say about the Rn value? 0. Yeah. Now I would be very impressed if you guys could tell me what theorem that is a demonstration of. Because it's actually a theorem that you're first introduced in AB pretty early on, and we don't really talk about it a whole lot. Hey, good job. It is the squeeze theorem. Sometimes it's called the sandwich theorem. So by the squeeze theorem then, we can say that the limit as n approaches infinity would also be 0 of our expression. And that pretty much completes the proof that the sign of x is going to be convergent everywhere. So hopefully this helps out.